Fielding questions by N.K. and Richard. Introduction. In this lab, we tested the magnetic field a small bar magnet produces across varying distances. This is because the magnetic field of a dipole decreases with distance. And using the Firefox app, we were able to take accurate measurements of the magnetic field of the small bar magnet to calculate the magnetic dipole moment. Using the data gathered, we are able to calculate the amount of valence electrons in alignment, as well as the amount of current to make a small solenoid of a similar magnetic dipole. To identify the dependence of distance for a dipole field, to demonstrate understanding and formulation of computational software, and to determine the dipole moment for a bar magnet. The experiment. Lab began with finding a magnetometer in the phone, which we used Firefox for. Then, figuring out magnetic north specific to the Bernal Science Building, we used the Firefox app to determine the degrees of the y and x coordinates. We then were able to collect data based on the distance of the bar magnet at different distances from the magnetometer. We were then able to use Excel for formula calculations and determining the dipole moment, which then allowed us to determine the strength of the solenoid. And finally, we were able to calculate the number of aligned valence electrons. Math behind the scenes. To calculate the magnetic dipole moment, we use the equations for the parallel magnetic dipole moment as well as the perpendicular, while plugging in the numbers in the Excel sheet. This led to us having a result of 0.1377 AM squared. If we were to have a current run through a single loop to have a similar magnetic dipole moment, it would have to be 10,957.A amperes. And to wrap a 20 gauge wire around the magnet, we would only be able to complete 12 loops. So to create a solenoid of similar magnetic field, we would have to run 910.7 amperes. The total number of aligned electrons resulted in 1.49 times 10 to the power of 22. This results in a percentage of spin-up atoms at 95%. In the Excel sheet, we plugged in the magnetic dipole moment as well as the distance, and subtracted it from the Earth's magnetic dipole moment as well. This allowed us to reach an average of 0.1377 AM squared. And by looking at the graph, you are able to determine that the distance affects the magnet in an exponential way. So when it is closer, it has a bigger magnetic dipole moment. Results and conclusions. Our calculations helped us determine that a solenoid of 12 loops with a current of 910.7 amperes would make an equivalent solenoid to the previous magnetic dipole moment. We were also able to conclude that the amount of aligned valence electrons was determined to be 1.49 times 10 to the power of 22 electrons, as well as use the Firefox app to find the magnetic north and determine the distances for dipole fields to yield a better understanding of the magnetic dipole moments and the factors that can affect them, including the Earth's own magnetic dipole moment, as well as used Excel to create formulas and be able to view the data on a graph.